Hello guys, in this video we will learn about the types of polarizabilities. These are of three types: electronic polarizability, ionic polarizability and orientational polarizability. In this video we will study the electronic polarizability. This polarizability occurs when an electric field is applied on an atom which has positive nucleus and is surrounded by the electrons. And due to this electric field, what happens? The spherical symmetry of the atom gets deformed. Now we will derive an expression for the electronic polarizability. The electronic polarizability is denoted by alpha E. Okay. Now we will consider an atom with positive Ze nucleus charge, which is surrounded by an electronic cloud, and its charge is minus Ze. In this condition, the charge density of the electrons is given by rho is equal to charge upon volume. Here charge is minus Ze, so it will be minus Ze upon 4 upon 3 pi r cube, which is the volume of a sphere, since the electronic cloud is in the form of a sphere. Now we will consider, this was the situation when the electric field is 0. Now we will consider a situation when the electric field E is applied on the atom. Now when the atom is placed in this electric field E, both the charges experience Lorentz force, means the nucleus and the electrons will feel the Lorentz force, since Lorentz force is given by QE plus QB. Here we only have the electric field, so the Lorentz force will be equal to minus Ze into E. Ze is the charge. Here we don't have the magnetic field, so we will only have the term QE. Okay. Due to this electric field, the positive nucleus and the electron cloud will suffer displacement. Let the displacement be D. Okay, this is the displaced position, and this was the original position. Here the nucleus and the electron cloud both are pulled apart. Okay, now as they are pulled apart, there will be a restoring force between them. Now the Lorentz force, which is equal to minus Ze. Okay, this is applied, and the restoring force will be equal to the Coulomb's force, which is given as the charge of the nucleus into charge enclosed in sphere of radius d. This one, let the radius of this sphere be d, upon 4 pi epsilon naught d square. This is the formula of the Coulomb's force. Now here we have to find the charge enclosed in sphere of radius d. So we will find this charge by the formula of charge density, which is since the charge density the charge density is given by charge upon volume, so we get the charge equal to rho into volume. Therefore the charge enclosed will be rho into 4/3 pi d cube. Here d cube is due to the sphere of radius d. Now we had derived the equation, this one, rho is equal to minus Ze upon 4/3 pi r cube. So from here we can write the value of rho as rho equal to 3 minus 3 upon 4 Ze upon 4 r cube, sorry, pi r cube. Okay, so we will put this value in this equation. So our charge will be 4/3 pi d cube into minus 3 upon 4 Ze upon 4 r cube. Okay, now our charge becomes, this 4 will cancel out with this one, 3 will cancel with 3, and we get the value Ze d cube upon r cube. This is a charge enclosed in the sphere of radius d. Now we will put this value in the Coulomb's law, which is the F restoring equal to Coulomb's force, which is Ze upon 4 pi epsilon naught d square into minus Ze d cube upon r cube. We have put this value of charge in this equation. Now we will consider the equilibrium case. In equilibrium, both the forces will be equal, that is the Lorentz force will be equal to the restoring force. Okay, so this becomes, Lorentz force was minus Ze into E, and this restoring force is minus Z square E square d cube upon 4 pi epsilon naught d square r cube. Now we will further solve this equation, and this minus will get cancelled with this one. Now we will find the value of d from this equation. So d becomes 4 pi epsilon naught r cube into E upon Ze. Here Z cancel outs with this, E cancel outs with this one. So we get this equation. Now from this equation we get that the displacement is directly proportional to the applied field. Okay, from this equation. Now the two charges plus Ze and minus Ze are separated by a distance, therefore they will act as if they are electric dipole. Due to this, an electric dipole moment will also arise, that is P, which will be equal to charge into displacement. So the dipole moment comes to be, charge is Ze and d is, from this equation, 4 pi epsilon naught r cube E upon Ze. This will cancel out with this one. So the dipole moment becomes 4 pi epsilon naught r cube into E. From this equation we can we get that P is directly proportional to the electric field, that is the dipole moment is directly proportional to E. So uh, we will solve it further. We'll get P is equal to alpha E into E, which is the proportionality constant. Here alpha E is the proportionality constant and is the electronic polarizability. Okay, its value is equal to 4 pi epsilon naught r cube. We've got this value from this equation. So uh, we have the equation, this one. From here we get that the restoring force is directly proportional to the displacement. Okay, we know that when the force is directly proportional to displacement, it is the case of simple harmonic oscillator. Okay, we can therefore we can consider this system as the harmonic oscillator, where f is equal to minus kx and x is the displacement. Okay, we can consider this system as that of a harmonic oscillator, because in this system we have got that the restoring force is directly proportional to displacement d. Okay, now we will find out the equation of motion of an electron bound harmonically to an atom in an oscillating field, which is E naught e the power iota omega t. We have considered an oscillating field, this one, that we have considered that the electron is bound harmonically in this field, and now we will find out the equation of the motion of this electron. So we know that the equation is d2x by m into d2x by dt square. This comes from f is equal to m into a, okay, and plus m omega naught square x. This is the force due to when the electric field was not there, and which is equal to E into E naught exponential iota omega t, and this is the electric field applied. So here the m is mass of electron, omega naught is the natural frequency of oscillations of electron. Here this force comes when there is no electric field, and here the omega is the frequency of applied field. Okay, and E is the charge on an electron. Now we will suppose that the solution of this equation is x equal to x naught exponential iota omega t. We have considered that the solution of this equation is this one. So we will get that m omega naught square minus omega square x naught is equal to E into E naught. We have solved this equation, and therefore we have got the final answer, this one. From this equation we can find that x naught is equal to E into E naught upon m 1 upon omega naught square minus omega square. Now we will find the amplitude of the dipole moment. So it will be P naught is equal to, same here, the charge into displacement. Here the charge on the electron is E into displacement from this equation, E into E naught upon m 1 upon omega naught square minus omega square. So the displacement becomes E square E naught upon m 1 upon omega naught square minus omega square. Now we will find out the formula for electronic polarizability, which is given as dipole moment per electric field. We will put these value in this equation, which on solving we will get upon E naught. Here this is E naught. We will cancel this one. So our final answer becomes E square by m upon omega naught square minus omega square. This is the equation for the electronic polarizability. Now from this equation we get the dependence of alpha on frequency. From here we get the dependence of alpha on the frequency omega. So here we will end the video. I hope you like the video. Thank you.